Welcome back to the next segment of our review. This is review video number 10, and it is all about kinetics. This video is based off of New York State's chemistry curriculum with the intent of covering the major parts of every unit, not everything, but the major stuff that you will most likely see come time for your Regents exam. So, let's do it. In kinetics, we're talking about chemical reactions. What makes them fast, what makes them slow, what makes them happen, what makes them not happen. And all of this has to start with the fact that a reaction occurs due to something called an effective collision. All right? Effective collision. Effective collision. An effective collision is based off of two things as well. It's based off of energy and orientation. Okay, so if two molecules can react with one another, they have to all collide, number one, but that's just not good enough. They have to collide with the proper amount of energy and the correct orientation of the molecules in space. All right? So that's something also to be on the lookout for. An effective collision has to have the right energy and it has to have the right orientation. That is what collision theory is. So we can make reactions happen faster or slower by just simply increasing the frequency of collisions. The more times a molecule collides, the more likely they are going to be effective. It's just basic probability. So the more frequently they collide, the better. Effective collisions. All right, between the reactants and, let's see, what does this say? If the frequency and the effective collisions between reactants increases, there we go, the rate of the reaction is going to increase. And it all comes back to probability. More collisions, faster reaction. And there's many ways that we can do this. Some of the most common ways have to do with the environment, right? So we can increase the temperature. Now, you need to ask yourself, we've talked about this, even if you've only been following this series, and you haven't been really letting chemistry soak in throughout the year, you should know by this point that increasing the temperature means that the molecules move faster. Okay, so take that information and ask yourself, if molecules are moving faster, will there be more frequent and more effective collision? And the answer is yes, right? Increasing the temperature increases the rate of reaction because the molecules are moving faster. Again, if you've been paying attention, we've talked about it maybe once or twice. Pressure. Pressure has to do with force. And if we increase the pressure, what we're doing is pushing the molecules together. So again, ask yourself, all right, if the pressure is increasing and the molecules are moving closer together, do I expect the frequency and the effective collisions to increase? Yes, right? They're closer together, they're going to hit each other. I always like to refer to these molecules and this topic with kids in the hallway or kids in the gym, right? Increasing the pressure is like taking your gym size and cutting it in half, leaving the same amount of kids running around playing basketball or badminton or whatever it is they're playing. If you take the same amount of kids and cut the gym in half, there are going to be more accidents because kids are going to collide more often. The same thing happens with molecules. Increasing concentration. That means just simply there are more molecules. And if there are more molecules, again, you would expect there to be more collisions. It's simple probability. More molecules, more collisions. Increasing concentration also increases the reaction rate. Now, the one that doesn't have to do with environmental factors, but it has to do with chemistry, is adding a catalyst. What a catalyst does is it improves the likelihood of an effective collision, whether it's orientation or energy. It allows the molecules to collide properly if they would have otherwise not done so. But by definition, a catalyst is creating an alternate pathway. And by definition, for our curriculum, it lowers activation energy. You might remember that during this unit. You might not know what activation energy is, right? You might not remember. I'll get to it in a little bit, but that's by definition for our curriculum what it does. But what it does in the chemical logical term is it just helps the molecules get pushed together right. So a couple other things that we need to think about and put in our brains are the terms endo and exothermic. Endothermic, we've talked about this in this series as well. Endothermic reactions absorb heat. Endothermic reactions absorb heat. And what happens is the potential energy of the products is greater than the potential energy of the reactants. I'll explain that more once we get down to the graphs below. Okay? But this leads to a delta H value being positive. Okay, delta H being positive. And delta H is the heat of the reaction. Okay, so heat of the reaction meaning energy of the reaction. If a reaction is endothermic, it's absorbing energy, it's absorbing heat. So naturally, an endothermic reaction that absorbs heat is going to increase the amount of energy over the course of the reaction. So delta H is represented as a positive number. Exothermic reactions are the exact opposite in every way as far as this definition is concerned. Exothermic reactions release heat, release energy. Release. And because over the course of a reaction, if energy or heat is being lost, the potential energy of the products is going to be less than the potential energy of the reactants because we've lost that energy, and delta H is negative. The total amount of energy over the course of a reaction will be less than what you started with. And these graphs show potential energy curves. They show the amount of energy from a reactant to a product. So if we just look at them, we can see the difference between them, which is the reactants start low and end high in this one, versus the reactants starting high and the products ending low. These two represent two different types of potential energy diagrams. They represent the endothermic graph on the left, because energy has been absorbed. We have increased the amount of energy in the system, endothermic, and exothermic on the right side, where we see the amount of energy being less. It has lost heat throughout the course of the reaction. Okay, so that's the first thing that we can take from this. The second thing that we could take from this, if we were reading this with numbers on the side, is we could actually give values to these numbers, these locations. How much energy did I start with? How much energy did I end with? And that's actually how the delta H is calculated. Right? Yes, it could be positive. Yes, it could be negative. But if we were looking for an actual numerical number, you can see it's presented by the difference of the total energy. Two more things that are really important are activation energy and what the catalyst looks like. So we'll start with the activation energy, which I'm just going to write up here. Activation energy is the energy from the start to the top. The energy from start, reactants, to top. Now, when I say top, I don't mean end, right? I mean where that letter B and A are. Start to top. And this is the activation energy. No reaction can actually take place if a certain amount of energy is not involved, is not around the system, is not absorbed by the system. And this really has to come back to the original concept, which that my reactants have bonds. They have bonds. And if I want to change those bonds, we're going to have to break them. Regardless of the bond type strength, every bond absorbs energy to break. And so every potential energy diagram goes up before it comes down. And in this case, whatever this number is, the activation energy is the amount of energy required to break the reactant bonds. It is that much energy, and if the molecule does not absorb that much energy, no reaction will take place. Right? Back to what we said at the beginning. An effective collision has to have the proper amount of energy. This is that amount of energy that it's talking about. If it does not absorb this amount of energy, the reaction can't take place. Doesn't matter if they're in the proper orientation. It will not be an effective collision if these two amounts don't happen. That's called activation energy. And the last thing that we could talk about is the effect of a catalyst, which we said lowers the activation energy. So a catalyst works, and works very well, because what it does is create an alternate pathway from start to finish that doesn't require as much energy. Same process, reactants are unaffected, products are unaffected, but to get from point A to point B, A to B, the amount of energy required is less, and that makes the collisions easier to be effective. Same thing on this side. The catalyst goes up, and then it comes down. Starts in the same place, ends in the same place, but over the whole course of the situation, just requires less energy to start. So I hope this is a quicker video. It's a shorter unit. Really hope that helped you remember what was in the kinetics unit. Please do me a favor, like the video, subscribe to the channel if this is helpful, or if you just want to support me. I appreciate you, and I hope that you are getting something out of this to prepare yourself for the Regents, whenever that may be. Thank you so much. I hope I catch you in the next one, and you keep watching along.